A very good afternoon. So I'm not doing very well. My throat is bad, but I'll try and speak nevertheless. Can you hear me? So my throat isn't very good. I hope you're able to hear me. The lecture 6, we'll conclude our ML discussion on ML examples and then move on to the notion of subgradients. But to get into subgradients, we need to understand a little bit of quasi-convexity. So we'll encounter them en route. Okay, so this is the outline of content for today. We've almost done with the calculus of convexity and some more properties that we were building upon. And then we left a homework problem, which is understanding the convexity of some machine learning loss functions. I'm assuming that you would also have studied those loss functions for their so-called strong convexity and strict convexity. We look at direction vector, subgradients, subdifferentials, hopefully. But towards that, we'll have to first do epigraphs and sublevel sets and quasi-convexity. So you'll actually do quasi-convexity and then do first order conditions. And then, of course, subgradient calculus will come later. Okay, so this is where we kind of left off last time. We talked about the composition with vector functions. And the way we visualize this, the function h, which is applied on a function g, if the function g, function g, what would we expect it to have? Property g's must be convex or concave, but h must always be convex, right? But if the g is concave, then h is non-increasing to counter the effect of g's, right? So the thing you need to just notice in this composition, hg by default is convexity and non-decreasing. Okay, and the exception, this should be simple enough to remember. Exception, I should write it in. The exception is that concave g would mean non-increasing h. That should be good enough to remember here. And then we took some examples. Specifically, the example of log sum x being convex. I said this will require a special case of convexity, which is called midpoint convexity. So midpoint convexity says that, well, if for any function, if I can prove that f of x1 plus x2 is less than or equal to f of x1, sorry, half of x1 plus half of x2 for all x1, x2 in the domain, then f must be convex. Okay. So this seems to be a necessary and sufficient condition. So under this condition, we could show that log sum x is convex. This is where we concluded. And basically, this required us to invoke the Cauchy-Schwarz inequality, right? So we concluded with this as a recap. And a lot of it is just about substitution. For example, the exp of a sum is product of the exponentiated entities. And then when you take a log of this product, then you'll get basically a log of the sum of the products. Then you'll get a log of the sum of alpha I beta I, and that you can show is less than equal to the log of so the log of this sum is less than equal to log of the product of the sums. Log of sum of product is less than equal to log of product of the sums. And that's because the arguments themselves, the sum of the products is less than equal to product of the sums. Well, modulo square root, and that is Cauchy-Schwarz inequality. So how do you prove the midpoint convexity? That was a homework problem. How do you prove that? Well, you'll have to basically show that for any mu x1 plus 1 minus mu x2, if this holds, this inequality holds, then x1 plus x2 by 2, f of x1 plus x2 by 2 should be, oh sorry, I missed this by 2, f of x1 plus x2 by 2 should be less than equal to f of x1 by 2 plus f of x2 by 2. That should be straightforward, right? If it holds for all mu, it also holds for mu equals half. The other way is a tricky part. So if this holds, right, under all x1s, x2s, then to prove that f of mu x1 plus 1 minus mu x2 is less than equal to mu f of x1 plus 1 minus mu f of x2. This will require you to do some manipulation. You'll have to show that this right hand side, right, for some x1, x2 would correspond to the right hand side here for some different values of x1 and x2, right? So you'll have to show some correspondence between the left hand side and right hand side. How do you do that? Did anyone attempt this homework? You need to find that x1 tilde, x2 tilde such that mu of x1 plus 1 minus mu x2, mu x1 plus 1 minus mu x2 is the same as x1 tilde plus x2 tilde by 2. x1 tilde by 2 divided plus x2 tilde by 2. Why is that helpful? Then I can actually substitute for x1 tilde by 2 plus x2 tilde by 2 here. And then what happens? The right hand side is also by midpoint convexity, f of x1 tilde by 2 plus f of x2 tilde by 2. How does that help show this correspondence? Mu f of x1 plus 1 minus mu f of x2. One step is pending, right? Even if I find that x1 tilde and x2 tilde, how would I show that this inequality? So I can basically substitute for the argument on the left hand side. But then I need to show that this inequality holding for x1 tilde, so this x1 tilde, x2 tilde. So I have to show that this on the right hand side should give me a less than equal to mu of x1 plus 1 minus mu of f of x2. Any thoughts? Anyone thought about it? We won't be doing the class, but if you have, you can let me know. This is where the homework problem is. So are you guys attempting homework problems? You should. Okay, so I'll most of the time leave you at some point like this, and then you need to really complete it. Anyone thought about this homework problem? A very simple problem. No? Okay, so I would expect you to go back and complete this. Okay, so I will now move to the next, probably the last element of this calculus. So we, in terms of calculus, we talked about compositions. Okay, before compositions, what all did we discuss? Affine transformations. Two norms, three compositions, H of G, H, G. Anything else we discussed? So this is one more, which is pointwise maximum and supremum. Supremum is a generalization. It's a generalization of the pointwise maximum, and I'll explain what that is. So if you have multiple functions which are all convex, okay, so just take two for now. Okay, so if for every point here, for every point, if I take the maximum of these two functions, right? So let's just take for wherever it's visible, right? You'll find that, well, this part, right? Here blue and here red. They are the pointwise maximum across these two functions. So you can call them F1. And the one in blue is F2. Now, likewise, you could have multiple such functions. So the max of F1, F2, Fm is also convex. And let's understand this a little bit more here, right? So I've shown the same thing here. If I have multiple functions, if I take the pointwise max of all of those, it's basically like the envelope at the top, right? Earlier we talked about the case of matrix completion. You remember we talked about the spectral norm. So there's a kind of envelope, right? So this is like, that was envelope from the bottom. This is envelope from the top. So I've shown an example here. Let's say I take a vector x and I take the r largest components of x and I sum them up. The sum of r largest components can be presented as a pointwise max of multiple convex functions. And how do you do that? Well, basically, imagine that I have each function f1x is a vector v0 transpose x, where this v0 is basically some r components set to 1, all the remaining components set to 0. So what is f1 capturing? F1 is capturing the sum of some r random components of x. Okay. So what we are trying to say is sum of r largest components of x is max over sum of r random components of x, where this summation is over all such are random vectors. Is this clear? So this is sum of some r random vector, components of x, and this is one random vector. Over all such random vectors with r1s and rest zeros. That's what I'm saying. Only r of those components should be ones, the rest should be zeros. So E1 has r of them set to 1. Similarly, a V2 has r of them set to 1, remaining are 0. What are each of these functions? F1, F2. And how many such functions will be there? N choose R. So F1, F2, N choose R, all of them are what form of functions? Linear. All are linear functions. Affine functions of X. So basically, what is this? This is nothing but is max over V with R ones of V transpose X, right? If you say n choose R V's, max over n choose R V's with R ones and residues. Okay. Okay. So this is an example. Now, how do you prove that pointwise max itself is a convex function? How would you do that? For a finite number of such functions? Yes? I'm audible. First principles? Very simple, right? I mean, if I just look at this form, f of mu x1 plus 1 minus mu x2. Now, f is max of multiple functions, right? And each of those functions is convex. F1 of this convex combination is less than or equal to convex combination of F1s. F2 of this convex combination is less than or equal to convex combination of F2s, right? Just put these indices. F1, then likewise F2. For the same set of arguments, right? And if I take a max of the left-hand side, right? Max of the left-hand side, you can show that it is less than or equal to the max of the right-hand sides. That's it. Okay. Now, a generalization of this is when the indices are themselves possibly they may be countable, but they may be infinite. Let's say the simplest generalization is when the indices, right, max over I if I is. Now this index I becomes very large, potentially infinite. That's a generalization. And my generalization is not just max over I. I'll say, well, I'll make I itself an index and I'll call it Y. So this is my generalization. I say my index itself has now become an argument and max over the argument. Now potentially it could also become uncountably infinite. I might just make it real number, real value. So that gives me the notion of supremum. Right, so far we are talking about this is all maximum. So far, right, this is maximum. But this is supremum. Supremum. So instead of calling it max, I'll call it supremum. Why? Because a max is guaranteed to be attained. A supremum may not be attained. And that's especially true if you're looking at uncountably infinite. Right? Where? For supremum. So we are just saying the indices, the function. Here they will say F1, F2, F3, Fn choose R. Right? Finite number of indices. Now I'm saying the indices into the functions. There are lots of functions. I'll give examples. If the functions themselves become very large in number, and I am now trying to access those functions through an index. That index itself is, let's say, real value. Then I start talking of supremum and not maximum. Is that clear? So, yeah. Another question? Yes.
And like I think the possible variation methods for US won't be that. Like when you take the maximum, you might get the quality. So is it valid for piecewise functions or?
It's valid for any convex function. This is valid for any That's why you should try and write down. But from first principles, you can prove any bunch of convex functions is prove. Now, for suprema, it's going to be a little trickier, but for maximum, it's not difficult at all. Okay. Now, okay, so I'm defining my function. Supremum over y of f of xy, where fxy is convex in x for a fixed y. So y is fixed. Y is like an index. Just like in this example, f1 is an index, f2 is an index. So the moment I fix the index, my vector v1, v2 or vi gets fixed. So the function is fixed in terms of the index. Now I've taken a jump and I said, well, if fxy is such that fxy is convex in x for a fixed y, then I'm claiming supremum over y of fxy is convex. When? So when means if here. Okay. So you see the generalization. Now we won't. Okay, this is called pointwise supremum. This should be for every y in S. Okay. So this gx, I've just given it a new name. I can give it a new name here also. So it's called gx. Okay, and this y is in some S. Okay, so we're going to take examples. And the most classic case is that of supremum. Okay, supremum over real valued y. Okay, actually, I have not shown that. I put S there, but let's say Rn of the L2 norm of matrix X times the vector Y divided by the 2 norm of Y. Okay. So, I mean, if you want, you can think of this as X, Y square also. Okay, doesn't matter. Supremum of that. But, I mean, in terms of the maximizer, maximizer will be the same for square as well. But what is really happening? Now, intuition is important here. What's really happening? We're saying is basically, oh, by the way, this is for okay, for symmetric X. I forgot to mention symmetric matrix X. Okay, which is in R n cross n. So n by n symmetric matrix X. So if it's not symmetric, then we'll have to talk of something called a singular value. We'll see that in a very few soon. Right? The good point. If it's not symmetric, what happens? So yeah, good question. So the example is when g of x is this. So the the function whose convexity we are talking about is the G of a matrix. So the domain is the space of all symmetric n by n matrices. Correct. Okay. So what's really happening here? If you were to think of eigenvalue decomposition for x, you can, right? You do an eigenvalue decomposition. If x is not square symmetric, you could think of singular value decomposition. Again, these are things you should now remember, right? We have done this when we talked about and we motivated matrix completion. So this is symmetric. We talk about eigenvalue decomposition. And if you have seen PCA, what happens, right? PCA captures the direction of maximum variance. So if you were to expand it, like if you were to look at this as a square root of y transpose x y, that's one way of looking at this 2 norm, right? It's a square root of. So if you want, you can just expand this part. So I don't want to be lost in this. So I'm assuming you guys have looked at previous year's notes, but this is basically y transpose x y square root. This part will do. The part in similarly, the denominator is also square root of y transpose y. So if you think of, given my y's and my y's are indices, so I would like to make the best use of my index y. So if think of this as restricting the norm, why are we putting in denominator? I want to restrict the norm of y. Why should not? I don't want to pump up the numerator just by saying, oh, I escalate y. Y should be controlled. So the denominator is trying to put control. You've seen, right? Regularization. Regularization is to regularize. So this is not dividing. In fact, when we talked of RLHF, we talked of two formulations. One involved a division by the what is it called? The base model, right? So here we're just dividing it to regulate the norm of y. So if the intuition here is that if I had to do a decomposition of y of x, eigenvalue decomposition of x, I would invest all the weight along the direction of the maximum eigenvalue, the direction of maximum eigenvector, sorry. The direction of eigenvector with the maximum eigenvalue. That's where I would invest all my right. So like here in the point-wise maximum, what we did was max over v in permutation of ones and zeros x transpose vx. So that gives us basically right max over linear. Here what I'm doing, here I'm considering the symmetric matrix, which is diagonizable x, and we look at lambda in the direction of the maximum variance obtained through the quadratic expansion of y transpose xy. And that direction will coincide with the direction of the maximum eigenvalue, right? The eigenvector direction corresponding to the maximum eigenvalue. And therefore, you would expect this, all the other y components to go to 0, only though that component which is in the direction of the maximum eigenvalue is the eigenvector direction to survive. So that's the reason we expect this to be a this value to be the maximum eigenvalue. Okay, is this intuition clear? So the question naturally comes, okay, this is fine if x is symmetric. What if x is not symmetric? What can I do? Yes. Sorry? Yeah. So will the same definition hold? See, here what happened was I use the same norm. The numerator norm is in Rn, denominator is also in Rn, right? But if x is not symmetric, if x is m cross n, what will happen? The numerator norm will be, sorry? Yeah, but the numerator norm in the numerator will be, if y is in Rn and x is m cross n, it will be basically in Rm. So you'll have Okay, now so we already kind of generalized. Now I'm going to do one more level of generalization. Okay, one more generalization. What if instead of this supremum, I say, well, any norm, I apply any norm, and I'm going to change my matrix. I'll just change the notation a bit also. Oh, sorry. X in is some norm of AX and some other norm of X. It can be some other norm. For example, this might be N and this might be N tilde. Actually, there should be N. It should be N only in the sense I don't want to use, of course, one norm in the denominator and infinity norm in the numerator. What I'm saying is they could be in different spaces. That's all. It's the same kind of norm in different spaces. So that's a next level generalization. Okay, so this is called MNA. MNA. Give it a name. So this is a matrix induced vector induced matrix norm. This is a matrix norm, vector induced matrix norm, vector norm induced matrix norm. N is a norm on vectors. I've induced a matrix norm. So this, as a generalization of what I showed just earlier, this is actually also a norm. Now I have a norm on matrices, which is also a norm and therefore a convex function. Okay. Okay, so I've given now the board. I'm going to just focus on intuition. Okay, so let's take the example. The first example. Just look at n equals 2 norm, which is where we began earlier, right? All I've done now is the numerator can be on Rm, the denominator can be on Rn. Okay, so I'm just going to change the one on the right. That's a small modification. Write it here. So example. So what does this mean basically? You're looking at the 2 norm of A is supremum over X in S, 2 norm of AX divided by 2 norm of X. So just remember that this X could be in Rn, X is in Rn, A is in Rm cross N. So now we just generalize from the right hand side. Okay, just look at this. Don't look at the part below. Just look at this line. If N is the 2 norm, right? All we are saying is here we had a eigenvalue, max eigenvalue. If you do a similar expansion, y transpose x transpose xy, you will basically land up getting a singular value. So remember that for symmetric matrices, square symmetric matrices, obviously symmetric square matrices, the singular values are nothing but the square root of the absolute value of the square root of the eigenvalues of eigenvalues basically. So in general, okay, so this turns out to be the sigma max of A, maximum singular value of A, which is nothing but the square root of the eigenvalue of A transpose A, right? All we are asking you to recap is, if A is a square matrix, like on the right hand side of the board, then the sigma max of A would have been the square root of the lambda of A transpose A, like here. But the lambda of A transpose A would have been what? lambda square. And therefore the square root would have been absolute value of lambda. So that is a special case. Right? This is nothing but, if you want, you can write this as, okay, we are going a bit slow. We need to make this a little faster. Max, lambda max. So if x square is symmetric, then lambda of x transpose x is the same as lambda of x in the absolute in magnitude. Okay. That's how the generalization. Yeah. If you take the infimum instead of supremum of what? Of this form, supreme. Will it be convex function? Is that your question or? No. Not necessarily. There's a caveat there. No. We can discuss offline. Yeah. Yeah. Minimum is not a convex. So now coming back to other forms. So if you take the argument matrix to be identity, you can easily verify that if I put an identity here, n of ix divided by n of x is 1 always, right? Mn I is always 1. If I take n to be the one norm, these are special cases. Again, I'm not going to write all that on board, put it on the slide itself. Right? If n is the one norm, then this is where again you should start visualizing matrix algebra. What is AX doing? AX is just taking the columns of A and their linear combination using X, right? So column 1 of A into its linear combination into X1, column 2 of A into into X2 and so on, right? Now, if n is one norm, which means the denominator we are saying, I want to regulate the sum of absolute values of X, right? If I want to restrict the sum of absolute values of X, then where would I invest more of my absolute value? If I have to say, well, the sum of absolute values should not exceed 1. I'll say, well, I'll put all my value in that component for which the column has a highest one norm, right? Because I want to maximize the one norm of AX, which is basically maximizing the one norm of the sum of some of the columns of A. So this basically says, I've written this in words, if x1 is 1 and we would like the one norm of the linear combination of the columns of A, we would pick that x which has 1 only at the most important or the max entry and 0 at other places. Basically this column with the maximum one norm is what I should pick up. Rest I should not pick up, given my limitation of one norm. So makes sense for the peak to be where the one norm of A's columns is the highest. So basically, if you take n to be one norm, then the corresponding matrix norm of A is max over J, right? Which means max over all the columns. The column which has the highest one norm. Is this clear? Okay. So the intuition here. And you can verify that similarly, if n is infinity, then you'd say I'll pick up the row with the maximum one norm. But because when n is infinity, we are basically saying what? You're saying, well, pick as many entries because infinity norm just picks the maximum absolute value, right? Infinity norm doesn't bother if all the elements have the same value. So typically when you're looking at maximizing infinity norm, you'll just set all values to that same max value. Nothing to lose, right? So then basically that you can verify. That will basically amount to taking the row with the maximum one norm. So these are special cases. So, I mean, as a homework, you have to, if it's not clear, you need to read this and make sure you understand it. But I think I've provided enough intuition here. Okay. Is the eigenvalue of A transpose A, if it's real, yeah, it should be. It should be. Yeah, if A is real, should be real value. Okay. So there's one more variety of norm which basically has got made inspired by all of this. And now there are multiple ways we are now approaching some norms, right? One way to approach the spectral norm was as a matrix induced norm under L2 norm. Another way of looking at the spectral norm. Okay, here is given there. So yeah. I didn't mean to highlight this. So this P in other way of looking at the spectral norm, which is the max singular value of A, is by looking at it as the sum of all the singular values. Okay, the sum of all the singular values of the matrix A. So if you let this aside, I mean, not sum in the sense, the pth norm of the vector of singular values, right? But if P is infinity, then it becomes the max singular value. So the Schatten P norm is another generalization. Again, I repeat, which is nothing but the pth norm of the vector of all the singular values of the matrix. If you consider P to be infinity, then you're basically taking the max of all the singular values, which coincides again with the spectral norm. This is a spectral norm. So spectral norm is a matrix induced norm. It's also a Schatten norm, but under different values. It's a matrix induced norm under L2, and it's a Schatten norm under P in infinity. There is another interesting norm which we have seen earlier, which is a nuclear norm. What is nuclear norm? It's a sum of all the singular values. Okay. So far, what we are discussing, this is like max. This is always max. Spectral norm is max. But what we have seen earlier, when we wanted to approximate the rank of a matrix, right? We looked at the sum of singular values. And you remember sum of singular values was a convex envelope. I mean, we said, and you believe that it's a convex envelope around the rank function. But what is it actually? It turns out that the nuclear norm is the Schatten norm for P equals 1. The sum of all the absolute values of singular values is the Schatten norm for P equals 1. Okay, so that by virtue of being a norm is convex function. Okay, we are not giving proofs because intuitions are being provided.
So like you said that when P tends to maybe become a spectral, why is it written that P belongs to the range 0 to 1 itself? In that the definition.
Yeah, I mean, so that's a good point. So it's called, I think that it's just a notion. It's called the Schatten norm for P in 0, 1. Right? So if you just forget the name Schatten norm, then the sum of all the singular values, I'm sorry, the vector of all the singular values under infinity norm is a spectral norm. So not much in a name. But I think some texts also use the Schatten P norm for P independent of 0, 1. So good question. Yeah, maybe I'll update the notes and just drop this P in 01. So not a, that's just for the name, for the definition. Any other question? Okay, so again, I just want to reinforce that under P is in, I mean, this infinity norm of the singular values coincides with the 2 norm under the matrix induced norm when you look at supremum. Okay, now with all of this, we should be in a position to talk about convexity or strong convexity or whatever of all the functions we've discussed so far. So hopefully you give some time to this. Any reflections? L1 regularized logistic regression. Is it convex? Is it strongly convex? L2 regularized logistic regression. Is it convex? Is it strongly convex? Yes, what's your take?
We had we have a function, so some lots of exponential contact, and we have seen that we add plus lambda, and when the whole function becomes convex.
Correct. So log sum x, we have seen that it is convex, and just the addition of a strongly convex component will make the whole function strongly convex, right? If you add just L1 norm, it will not be strongly convex. Okay, so just to convince you that this is actually log sum x, right? So log of 1 plus exp minus yi transpose theta transpose xi. Think of this 1 as log of minus yi transpose 0 transpose xi. This is a vector of 0 that gives you 1. So it's still log sum x. And the proof is basically the generalization of the log sum x proof, where GIs are either zeros or linear functions. Right? So this is convex for sure, strongly convex under a specific condition. I've just the same set of expressions I had. If you want to do it from first principles, I've kind of written it down again, but it's basically the same. Now the only difference is that earlier we had alpha. Remember, we had a much simpler term here. Now we have the exponential, yi transpose yi into theta transpose xi. Right? That's the technique argument of earlier you had a simpler expression for exp. That's the only thing that has changed. Otherwise, yeah, and because of that, the alpha. Now you will also have a lot of these thetas, a lot of theta vectors, right? So sum over theta of exp minus yi theta transpose xi. So that will also mean that the index theta will sit into the alphas and betas, remember, which we use in the Cauchy-Schwarz inequality. So just to let you know that things have become more complex, lot more indices, but the form is the same. It's log sum x. So it's always worth going through carefully. And often we just, the complexity increases just by virtue of adding an index. Like we added an index which was kind of real valued, and that gave you the supremum. Okay, otherwise it's the same, nothing more. I mean, what you have on the left hand side is the LHS, right hand side is the RHS. RHS has a log of the product of the sum. On the left hand side is log of sum of the product. Exactly otherwise like earlier. And basically we have used the midpoint convexity. We have taken mu I to be half. So midpoint convexity again is what was used earlier. Nothing new. Okay. And yeah, we have invoked that a function is convex if and only if it's midpoint convex. That we have. So this is just proving the whole thing again by first principles, but not really required if you have registered the earlier proof of log sum x. Okay. Same thing. Now I've just brought back midpoint convexity. What does it mean in the context of the slightly more enriched form? Okay. So next, L1, L2 regularized SVMs. Are they convex, strongly convex? Any property that we have showed, any property from the calculus of convexity that we can invoke? Yes. Something sitting right on the board here. Max, right? Max of 0, 1 minus yi theta transpose xi. And then there's a sum of multiple maxes. Right? So what's really happening is max of a constant, comma linear. So constant is always convex. Linear is also convex. And we already given the graphical intuition earlier. You can do it by first principles. And then, of course, a sum of multiple convex functions. Okay. And then lambda times norm theta, that should be also no different from earlier. Okay. The third, L1, L2 regularized multi-class logistic regression. Yes. Anything completely new that's happening here? Is it similar to any of the previous cases? So don't be scared. Speak out, right? It's perfectly okay to be wrong, but you should try. People who have especially not spoken. Sorry? You're saying something is missing here? Uh-huh. Okay, did I? So there's an classes C, xi outside. Okay, this is no, sorry. I think good point. This is not supposed to be there. Okay, let me. Thankfully, I can. Sorry, I'll just hide this. This should not be there. I will hide this. Is that okay? So anything? Yeah. So theta yi. I think I made some. Sorry, yi into theta transpose xi. Yeah. So this is, please treat this to be. There's a little bit of goof up I made. Yeah. Thanks for pointing it out. See, the thing is here there was a 1. I think the main difference is what in the logistic regression there's a 1 basically which corresponds to theta's being 0 for that class. So there's theta 1, class 1, and theta class 0. I mean, in some sense. Right? So this 1 comes from there. Now what have we done? The only difference is instead of this log of 1, right? We have multiple classes. So this should have not been there. I think we should just get rid of this. It's already covered. I think I think I just hide this also. Yeah. I think I didn't pay too much attention. Okay, is this okay? There's a yi missing out here. So there should be a, how should the yi manifest itself? Let's write this down. So you should write it down. We've done this logistic earlier. How should yi manifest itself? So earlier yi was 0 or 1. Now we have yi coming out as a index into the class. So only the theta corresponding to that yi will matter, right? Okay, but effectively, what should this be? I mean, given that multi-class logistic regression is a generalization of logistic regression, it should also be convex, right? Basically, what we'll have is log sum x with summations of a lot more indices. That's all. So you can ignore this part and this part. I'll kind of correct this, but I think the idea is exactly the same. Okay, so I'll skip to the next one. What about least squares? That should be the easiest of the lot. What should happen to least squares? Is it convex? Right, it is convex. In fact, it's a composition of quadratic with or a linear with quadratic, right? Composition of quadratic with an affine function. So there's an affine inside, then there's a quadratic, and then there is again a summation. Is it strongly convex? Okay, so the first component is actually always strongly convex, right? Even if you use an L1 loss here, this part is always strongly convex. So you don't need a L2 loss in the case of least squares. In fact, if it is L1 regularized, it's called lasso. What about matrix completion? Is it convex? Do you think it's strongly convex? So there are multiple bi's that you need to match through the corresponding AI. Right? AIs are known, YIs are known. All you're trying to estimate are the X. Minimize the completion on it. I mean, minimize YI minus AI X so as to complete X. That's the whole objective. Such that X is as simple as possible. Simplicity is measured through the nuclear norm. So what is your observation? Yes? Sorry? Nuclear norm is convex, just and then the other part? Any composition property? Does it look affine in the X? It's affine in X. I mean, you could think of X as matrix, but it's also can be viewed as a unrolled matrix into a vector. That's also a view. Right, from that perspective, it is affine only. Affine. Norm composed with affine. Right? That's exactly what it is. Okay, so affine composed with L2 norm, and we already seen this part is a Schatten norm, special case of Schatten norm, or it could also be seen as example of pointwise supremum of finite number of sorry, infinite number of convex functions. It's infinite, not finite. Yeah, I made a mistake. It's infinite. Okay. There's one more left. Softmax contextual bandits. What is your take on this? Is this convex? Yes. Which one are talking about? Matrix completion. Y is a vector. A is also A is a matrix. X is a matrix. Oh no, I mean Y is also vector. It has compatible dimensions. So A is actually So thanks for A could be a matrix. A could also be a vector. So depending on what form Y is. So it depends on what you're trying to match. So some summary statistics. So X is a matrix. You're trying to complete it such that some summary statistics associated with X are matched. That's it. I mean, so it doesn't really matter so much as far as convexity is concerned. Okay, so what about this softmax contextual bandits? Does it look like a loss, or does it look like some likelihood? Likelihood? Sorry? It's not convex. Do you think it's concave? So you're saying this is neither convex nor concave. Just because it's a softmax?
Convex.
Hmm. Hmm. So numerator you're saying is convex. So is this possible? Is it possible to view this as a likelihood? Okay, so I have some question here. So this is going to leave you with some food for thought. The regularized logistic regression loss is actually a cross entropy loss, and it has a corresponding likelihood, right? So if you have done logistic regression in your machine learning course, you're trying to maximize the posterior likelihood, and that is equivalent to minimizing some cross entropy loss. So what you're trying to minimize, you would like it to be convex. But the likelihood that you try to maximize, is it concave in the case of logistic regression? So I have a similar question here. Okay. So the softmax contextual bandit, I mean, this, you remember this PI and all came as inverse propensity estimate of the reward. So we may want to worry more about maximizing than minimizing. But are we, question is, are we interested in maximizing or minimizing? Maximizing. So would concavity help more than convexity? I mean, obviously, yes, right? That doesn't mean we should we'll prove it to be concave, but some food for thought, and that's why I've drawn a parallel with regularized logistic regression. So think about it. Okay, we'll need to move on. Think about this last part. Okay, so strong convexity, I just want to put a word here. I mean, you saw the use of strong convexity so far has been, it makes something strongly convex just by adding a regularizer. If it's a squared loss, it is by nature strongly convex, right? And then there's also a strong convexity parameter mu, right? How strong the strong convexity is. And what basically strong convexity means is that there's a quadratic lower bound on the growth of the function. But we'll see more on the growth of the function when we look at its first order definitions. Okay, so we'll want to do first order definitions. Now, strong convexity doesn't imply that the function is differentiable at all. Like we saw the case of L1 regularized, sorry, L2 regularized hinge loss or SVM. SVM loss is not differentiable, though it is strongly convex when you have L2 regularization. Okay. And we'll see that a strong convexity is interesting because it results in faster convergence using certain descent algorithms also, which are designed for strong convexity. Okay. And this is an example we saw, hinge loss plus L2 norm is strongly convex. So which means that if a loss Gx is convex, we can derive a strongly convex loss just by adding the L2 normal, L2, some regularizer which is strongly convex. Okay, now we'll very quickly look at first, we want to move towards first order properties. That's where, as I said, a lot of growth, etc. will come in. So, but some things before that, like we'll quickly do the notion of direction vector. We should be again very 101 thing, right? And then we'll move on to quasi-convexity. It's also interesting, and then convex functions, epigraphs, and then we'll do first order convexity conditions. So a little bit of growth there to first order. So the first concept is of a direction vector. So when you are assessing how a function is changing, rate of change of a function, for looking at first order properties, you are often interested in the direction. So So kth component of the function x will be denoted by xk. And you will consider these cardinal directions u1, u2, u3. So at the arbitrary direction vector v at x is such that it has unit norm. So we are always interested in separating or disentangling the magnitude from the direction. So when we say direction vector, we mean direction vector, and there's no magnitude associated. So that's the reason we say it will have one norm. I mean, norm equals one. And we are talking about Euclidean norm here, Euclidean space. Yeah, right. Okay. But when you talk about steepest descent later on, we'll also say, well, you can think of other spaces. So currently, we are all back to Euclidean space, okay? Just for convenience of visualization. So a directional derivative is basically the rate of change of the function along a particular direction. So I consider a direction vector, and I look at how fast the function changes along the direction of the direction vector. If I have function like this, if I have this direction vector, I'll basically slice the function, right? And see how along the direction vector, and when I slice it, how much it changes. That's basically f of x plus hp minus f of x divided by h. The scalar h along the direction of v is a dv f of x, right? Now this expression, right, limit h tends to 0 of this difference divided by h, you will see that this basically, the rate of change can be viewed as a dot product between the direction vector v, the direction vector v, and the so-called gradient vector. The gradient vector is the vector of all the n partial derivatives. Now, how do I visualize this? I think the key is, how do I visualize the direction vector? Any suggestions? The direction vector here, v is clear. Right? What is this gradient vector? How do I visualize it? If you slice it along the vector, what would the direction vector look like? Are you sure it's a gradient along that curve? I mean, the fact that gradient descent gets used, why do you think gradient descent is used on functions for function minimization?
Gradient gives the gradient gives a direction direction for the
Correct. So it's looking at function values, right? What have I shown here? This is the function value f. This is x1. This is x2. The gradient vector should be visualized in which space? In the 3-dimensional space or a 2-dimensional space? In fact, this v also, sorry, I mean, we have shown it this way. V is basically also in the 2-dimensional space. Okay. This is v. See, v is, okay, I've shown this in 3 dimensions because the function is a function of 3 arguments in this case. But in this case, let's say v is f x1, x2, right? So v is going to be in the x1, x2 plane. So v will be looking like this. Okay, this v I already shown, this is x1, x2 plane. The gradient is also going to be in the x1, x2 plane. Let me use a different color. Right, so gradient will be something like this or whatever. What should this gradient try and encompass? Intuitively, it's in, first of all, it's in this 2-dimensional plane of the arguments. What should it try and encapsulate? Rate of change of what? Function, right? So the gradient, so this is v. The gradient is basically looking at the direction in the xy space, x1, x2 space along which the the function at that value has increase, right? In fact, locally, okay, so this is at a point called x star. Just give it a name x star. At x star, what is the direction along which the function has the maximum change, overall maximum change, right? So this is a direction in x1, x2 plane. What is this dot product giving you? The change that this function has along the direction v. This was the direction v in white. This is the direction of maximum change of the function, increase of the function rather. This dot product is projecting the direction of maximum increase on the direction vector along which you want to change the rate. So I hope this is clear to everyone. This intuition. Okay, I mean, I hope you don't get confused. Here I've actually shown the direction vector in 3 dimensions, whereas on the board it's the direction vector is in 2 dimensions. Okay, so this is the whole notion of a directional derivative. If fx is a differentiable function, the directional derivative along v at x is the gradient f at x dot product with v. So then I have a question, right? If f has a minimum at some point x star, let's say this, now we're all interested in minimizing functions, right? We'll go to optimization soon. So if I'm interested in minimizing at x star, then what would dv f x star be along v? In fact, along any v. So you have jumped. You said, well, the directional derivative will be 0 along any direction because the gradient itself has gone 0. Okay, but let's just take a step back. Should we not argue step by step that, well, if the point is a point of minimum, then the directional derivative along any direction should be 0, right? And it's but natural to achieve that the directional derivative along the cardinal direction. So what is gradient giving you? The directional derivatives along the cardinal directions. That should also be 0. Right. So this is a question. dv f of x star equals 0 for all v. Is that equivalent to saying gradient of f of x star is 0? Okay. So that's what we are trying to head to. Now, this, and if you can, maybe the slides are already given right earlier. It'll be nice if you put this in your notebook, this pictorial depiction. What are we trying to show here? So we're trying to also now, see here the function was all shown in R3, but imagine that I start looking at the so-called level curves. Okay, I'm now going to zoom into the x1, x2 plane. And I'm looking at, just projecting this here, looking at basically how is the function changing? And assuming that the function is actually increasing as you go towards the center. Okay, let's say the gradient f pointing along the direction. That could be a visualization. Now, this curve along which I'm saying the function has some constant value is called a level curve. So there are multiple level curves sitting out here. So I have drawn in shades, but you can imagine that there is a level curve out here. There's a level curve out here, and so there are all level curves stacked up. So when moving within a pink level curve, you would expect f dash x to be 0. Function is really not changing. Well, moving within similarly the black level curve, it's again 0. However, okay, this is C1 is along the pink curve, C2 is the value along the black curve. So if C1 is greater than C2, that is the pink curve has higher function value than the black curve, then I would expect that the gradient, right, if C1, um, what would be, okay, maybe a question to you, right? What would be the gradient at a point here on the pink curve? In what direction will it be pointing? Going by the argument we just had some time back. It should be pointing outward. Pointing, yeah, that appears to be right. Assuming C1 and C2 are very close by. So moving from pink level to curve to the black level curve, we do not expect f dash x to be 0 for sure. It will not, because there's some change. In fact, we expect f dash x to be less than equal to 0. And what do you expect the interiors of these convex curves, these level curves to look like? We expect them to be convex. If these are convex, the interior is also, the function is convex. Interiors would expect it to be convex. Now I have a slightly different diagram here, right? Well, again I have this level curve pink, and now the internal curve f of x1 x2 equals c2 has not changed. The shape has changed, right? So I have several questions here. First of all, can this happen for a convex function? Do you expect the behavior above for a convex function? Yes. Do you expect the behavior below for a convex function? The behavior below is not expected for a convex function. Is the behavior above behavior like the case above? Does it guarantee that the function is convex? Let's say this is what I observe. Level curves are always like this. They're all looking, interior is always convex. They're called sublevel sets. They're always convex. Does it mean that the function is convex? And does the case below imply that the function is not convex? You understand? There are two different questions being asked. Necessity and sufficiency of convexity of these level curves in terms of the original function. And then there are some other questions also I've asked. This is a very nice set of figures to have in your notebook. The increasing or decreasing nature of f dash x in a region, how would you connect it to the curvature of the function, the rate of change of the function? Right? We said we'll also now start looking at rates of change, first order definitions. So curvature of function. If you look at strong convexity, we had this parameter mu. I said that has something to do with the curvature of the function. How would that reflect in these level curves? Okay. So, so directional derivatives are important first of all, to help understand the geometrical implications of such level curves on the function convexity, but also how algorithms get designed, why certain algorithms work well, why some of them don't work well, why are some algorithms very sensitive, right? Is an upper bound on curvature good enough? Do you need a lower bound? In fact, that brings us to the notion of Lipschitz properties of functions. So Lipschitz properties are giving some kind of, upper bound, how much is curved. Strong convexity says it is at least this much curved. Lipschitz says it is at most this much curved. Right? So the rate of change, you see the rate of change across these level curves, having some lower bound, some control on how fast it changes, and some upper bound, right, can be helpful. So this is more for food for thought. And with that, I'm going to just conclude with this. So this is notion of sublevel set. I'm going to conclude with a homework problem. Right? So the sublevel sets of a convex functions are basically, if you remember, I showed this on the board the last class. L alpha f is x such that fx is less than or equal to alpha. Right? So those are the sublevel sets. These are the sublevel sets inside, right? So if the function f is convex, what was your intuition? Many of you had some intuition. If the function f is convex, you are saying that the sublevel set should be always convex. That's how you're confident, right? Interiors of these level curves from the previous picture, you expect them to be convex, right? As C is reduced to below C1, you would expect the level curves only tend to keep being contained inside. In textual description of what you expect. So the region inside is called a C1, and C1 keeps on decreasing. Right? So this sublevel set is a convex set. That's clear. And the proof of this, first principles. Okay, I will not spend time on that. But the proof is basically by first principles. Now I'm going to leave you with a homework problem. So there is another notion which is the epigraph. Okay, I want you to think about this. So this is epigraph. Epigraph operates in the function space. So if function is going from R2 to R, the epigraph is in the R3. Sublevel sets are in R2. And epigraph is basically all the points above the function. Right? So if the epigraph is convex, does it imply that the function is also convex? Is one question. Okay. I mean, the answer seems to be yes. If the function is convex, is the epigraph convex? Answer seems to be yes. And the proof is not at all difficult. Same first principles proof. If the sublevel set is convex, does that imply that the function is also convex? Right. So if some sublevel set is convex, it doesn't look convincing at all. Why should the function be convex? But I'm making a stronger argument. If all sublevel sets of a function are convex, is it implied that the function itself must be convex? Huh? You are confident? Okay. Some of you are confident that the function must be convex. So look at the negative of the Gaussian. How does the negative of the Gaussian look like? Like this. Okay. Inspect all its sublevel sets and find out if they're all convex. Okay. Or I mean, you can look at also simpler functions like this. Negative Gaussian is more complex. This is simple. Log of absolute value of x is less than or equal to alpha 1. Log of absolute value of x. So think of some simpler function. See if, right, there's a stronger connection between sublevel set convexity and function convexity, and epigraph convexity and function convexity for all epigraph. So sorry, for all sublevel set parameters alpha. Okay. So of course, epigraph is only one. There's no multiple epigraphs. Right. So if epigraph is convex, the function is convex, may be easier to show. But sublevel set you have to claim for all possible values of alpha. That's trickier. Okay. Think about it, and please look at now you have to start visualizing. Visualize the connection between the gradients, the rate of change of the function, and the shape of these sublevel sets and epigraphs. Okay, I'll leave you with this only specific homework problem. Thanks. One last thing. The next Monday, the next Monday, I will not be here. So I will request. I'm requesting if we can just reschedule that class to a Tuesday evening, the next Tuesday evening, not the coming Monday. I meant second or third. Is it third? So Tuesday evening, is that okay, you guys? Huh? 7 to 8:30. So post dinner is okay, or on Tuesday? Just once. I mean, I'll announce a venue. Okay, so not the coming Tuesday, but the Tuesday after that, instead of the Monday class. I have to travel for some work. So post dinner, could it mean 10? I mean 9:30? Is it okay? 8:30 you are done with your class. 9:30 will it be okay? Thanks.